Hello and welcome to Lifelong Learning with Fulvia. Today's lecture is part 1 in a 3-part lecture series on black holes, gravitational monsters. Black holes are some of the most fascinating objects in the universe, and they are the most extreme form of gravity as we understand it today. Almost everyone has heard of black holes, but what are they? In this 3-part lecture series, we will attempt to answer questions such as, what is a black hole? How do they form? Why can nothing escape their gravitational pull? And should we be afraid of these gravitational monsters? Once again, black holes are possibly the most mysterious objects in the universe. We can't see them. We don't know what's inside. They gobble up everything that comes their way. They allow nothing to escape, not even light. So, what are black holes? And if we can't see them, how do we know they really exist? So how will we answer these questions? Well, we will start with setting the stage in part 1, today's lecture. Black holes cannot be understood without understanding gravity, so we will take some time getting to know it. In order to understand the formation of black holes, we first need to understand the evolution of stars. We will start our progression of events that will lead us to black holes by seeing how stars implode at the end of their lives to form white dwarfs and neutron stars. We will see in Lecture 2 that understanding stellar implosion is the key to understanding the formation of stellar black holes. So in Lecture 2, we finally get to black holes. We will spend quite some time on stellar black holes, and then we'll talk about the groundbreaking discovery of gravitational waves, first detected from the merger of 2 stellar black holes. In Lecture 3, we'll talk about supermassive black holes lurking in the center of most large galaxies. And we'll end our series with black hole-related topics such as Hawking radiation, black hole evaporation, the information paradox, and a brief mention of quantum gravity. So let's begin our first lecture. Now, although a black hole is a black hole is a black hole, there are 4 types of black holes categorized by their masses. The first and most common type are stellar mass black holes. Their masses vary between approximately 5 and 60 solar masses. As we will see, they form from the gravitational collapse of very massive stars at the end of their lives. The second most commonly talked about are supermassive black holes, with masses greater than 1 million solar masses and up to several billion solar masses. These types of black holes are found in the center of most galaxies, including our own Milky Way. Although their formation is still not well understood, they seem to be related to the formation and growth of galaxies. Somewhere between stellar and supermassive black holes are intermediate mass black holes, with masses around 100 to 100,000 solar masses. Now, there are a few theories on their formation, but the first observational evidence was from the merger of 2 stellar black holes. The last type are mini or primordial black holes with masses much, much less than 1 solar mass. Although they have not been discovered yet, theory suggests that they may have formed shortly after the Big Bang, when conditions in the universe were characterized by extreme densities. Throughout this series, we will talk about each of these types of black holes. Okay, so let's start with a definition. First of all, let's clear up a common misconception. A black hole is not a giant cosmic vacuum sucking up everything that comes its way. A vacuum, by definition, is the absence of matter. We will see that a black hole is quite the opposite. So let's define a black hole. A black hole is a region of space where matter is compressed to such high density and the gravitational field is so strong that nothing can escape, not even light. So to understand this, we will focus on what we mean by matter compressed to such high densities and the gravitational field is so strong that nothing can escape. But we will leave the nothing can escape, not even light, to the next lecture. So let's start with understanding gravity. Gravity is part of our everyday life. It influences everything around us. It keeps us bound to Earth. It steers how things move. It shapes their structure. If you throw a ball, build a house, fly a plane, you have to deal with gravity. But gravity is not limited to our everyday experiences on Earth. It is gravity that keeps Earth in orbit around the sun and stars bound together to form galaxies. Gravity shapes the overall structure of the universe. And at its most extreme, it produces black holes. So what is gravity? Well, to start, we can think of gravity as a universal force of mutual attraction between all matter. The force of gravity is one of 4 fundamental forces of nature. Every particle of matter feels the attractive gravitational force according to its mass. The gravitational force is probably the force with which we are most familiar. If you were to ask anyone why a ball falls to the ground, almost everyone will answer gravity. The next familiar force is the electromagnetic force. It is responsible for keeping the electron bound to the nucleus to form atoms. The electromagnetic force is responsible for practically all of everyday phenomena, except for gravity, of course. Now, the last 2 forces are less familiar. The weak nuclear force is responsible for the radioactive decay of atoms. In other words, it allows one type of particle to change into another. And the strong nuclear force is responsible for holding quarks together to form protons and neutrons, and is also responsible for keeping protons and neutrons together to form atomic nuclei. The gravitational and electromagnetic forces are both long-range forces, although their strength both decrease with distance. While the nuclear forces are very short-range forces. They act on particles within the nucleus of an atom. Now, although the gravitational force is our most familiar one, you might be surprised to know that it is by far the weakest of the 4 fundamental forces. The strong nuclear force is 10 to the 38th. That's a 1 followed by 38 zeros, 10 to the 38th times stronger than the gravitational force. Now, despite being the weakest force, gravity is the dominant force when dealing with the universe as a whole and when dealing with very massive objects in the universe such as planets, stars, and of course black holes. So let's get to know gravity. Isaac Newton was the first to provide a description of gravity and to put forth a theory. This is the description of gravity with which we are intuitively most familiar. It is often said that Newton's theory of gravitation was inspired by the fall of an apple. He reasoned that if the apple always falls straight down towards the center of the earth, then the earth must draw the apple there. And if matter draws matter, then it must be in proportion to its quantity. Therefore, the apple also draws the earth as well as the earth draws the apple. Now, Newton contemplated on this drawing force, what we call gravity today, and was convinced that every object has a gravitational attraction to every other object, and that the same force that causes the apple to fall toward the earth also steers the moon in its orbit around the earth. Newton's greatest insight is that the same laws that govern motions on earth also govern the motions in the heavens. In other words, he provides a link between the everyday phenomena on earth and the far-off cosmic phenomena. Newton's theory of gravity is called the law of universal gravitation and is described as a universal force of attraction between all matter. Here it is in its equation format. Now, equations are simply an elegant way of expressing an idea with just a few symbols. I will show a few equations throughout these lectures, but we will focus on the ideas behind them and not on the math. So in words, the force of gravity between two bodies is proportional to the product of their masses, m1 times m2, so the larger the masses, the stronger the force, and inversely proportional to the square of their distance. So if you double the distance, the force goes down by a factor of 4, and if you triple the distance, it goes down by a factor of 9. G is the constant of proportionality called the gravitational constant. Now, as you can see here, it is a very small number. So once again, gravity is a very weak force. It is only when dealing with very massive objects that it becomes the dominant force. So Newton's greatest insight is that the force of gravity works throughout the whole universe. In other words, every particle of matter exerts a gravitational attraction on every other particle of matter. Newton's law of universal gravitation is an excellent description for everyday gravitational phenomena both on and off Earth, to include placing satellites in orbit, launching spacecraft, studying the motion of most planets around stars, the motion of stars in a galaxy, and even the motion of galaxies within a cluster. But his law also has limitations. Most importantly, it does not give a cause for the gravitational attraction. In other words, it does not really explain what gravity is. Now, Newton himself remained perplexed by this action at a distance, so much so that in the third edition of his most famous work, the Principia, he wrote, "I have not been able to discover the causes of those properties of gravity from phenomena, and I frame no hypothesis." Now, for the purpose of this lecture, another limitation is that Newton's theory of gravitation cannot explain black holes. To understand what gravity is and to explain black holes, we need a deeper understanding of gravity. Albert Einstein would be the one to provide us with that deeper understanding. In 1905, a previously unknown patent clerk in a Swiss patent office published one of the most famous papers in the history of physics, which would eventually be known as the special theory of relativity, or just special relativity. In essence, special relativity is a relationship between space and time. As we will see, this is not as intuitive as Newton's ideas. Until this time, space and time were considered absolute. In other words, they were the same for everyone, and they were considered fixed, or they did not change. Space and time existed separately from one another. But Einstein changed all that. According to special relativity, space and time cannot be defined separately from each other. Instead, space and time are two aspects of the single continuum known as the four-dimensional space-time. Another non-intuitive aspect of special relativity is that space and time are no longer absolute. The measurement of space and time actually depends on who is making the measurement and how fast they are moving. We say that space and time are relative to the observer. Another important postulate upon which special relativity is based is that the speed of light is a constant. In other words, unlike space and time, which are relative to the observer, the speed of light is the same for all observers, regardless of the motion of the observer or the motion of the light source. And special relativity also contains Einstein's most famous equation, E equals mc squared, quite possibly the most famous equation in physics, if not of all sciences. In essence, this equation tells us that mass and energy are equivalent. In other words, mass and energy are interchangeable. They are essentially the same thing. Now, as groundbreaking as special relativity is, it does not include gravity. For that, Einstein needed to develop a new theory. He tried to incorporate Newton's gravity into special relativity, but in the end he realized that they were not compatible. In 1915, Einstein published his greatest work, The General Theory of Relativity. In the next lecture, we will see that black holes are a natural outcome of general relativity. The general theory of relativity is the current description of gravity in modern physics. With general relativity, Einstein radically changed our notions of space, time, and gravity. In essence, general relativity is a geometric concept of gravitation. Perhaps Einstein's greatest insight is that the very structure of space and time is dynamical. In other words, space-time can actually change. The very fabric of space is flexible. Einstein realized that gravity is something new. It is no longer Newton's mysterious action at a distance. The presence of mass and energy curves the very fabric of space-time. Now here is a two-dimensional representation where the grid lines represent space and how they are warped or curved by the presence of a massive object. Gravity, thus, is simply a manifestation of the curvature of space-time. The classic example is a bowling ball on a rubber sheet. The bowling ball will cause the rubber sheet to curve or warp, as we see in this diagram. If we then place a marble near that curvature, it is easy to visualize that the marble will move according to the curvature of the rubber sheet. So it moves toward the massive body not because of a force, but because the body has curved the space-time through which the marble must travel. In other words, gravity is the curvature of space-time. Now, it is not an overstatement to say that general relativity is the key to understanding the universe. It is the best description of the basic properties of space and time, the best description of how gravity works, and the best description of how the universe works as a whole. Gravity pretty much shapes everything in the universe. Some of its offspring are dark matter, dark energy, and of course, black holes. So space-time is shaped by the presence of mass and energy. What about light? If it's massless, is it affected by gravity? And the answer is yes. Light follows the curvature of space. So here we see the curvature of space-time produced by the sun. So light from a star in position A will bend as it follows the curvature of space, such that when it reaches Earth, it will appear to be coming from position B. This effect was successfully observed by Sir Arthur Eddington during the total solar eclipse of 1919. And this was the first observational proof of Einstein's general theory of relativity. We will see that in the extreme gravitational field of a black hole, space is so curved that it gets pinched off from the rest of the space around it, and light gets trapped in the extreme curvature of space. Now, this is the equation of general relativity in symbolic form. It is known as Einstein's equation. This is actually a set of 10 nonlinear equations, all tangled up and intertwined with each other, that describe the geometry of space and time. They are known as the Einstein field equations. But please do not let the symbols frighten you. Essentially, the left side tells us something about the curvature of space at a point in space, and the right side represents how much matter and energy is located at that point. And this is simply a constant. So in words, this equation tells us that the total spatial curvature is equal to a constant times the density of matter. So general relativity relates mass-energy density to the curvature of space-time. In other words, the density of matter at a point in space determines the total space-time curvature at that point. Since gravity is the space-time curvature, we can say that the density of matter at a point in space determines the gravity at that point. Now, this relationship was beautifully summed up by the famous physicist John Wheeler. Matter tells space-time how to curve, and space-time tells matter how to move. So let's do a quick summary of our understanding of gravity. According to Newton, gravity is the attractive force between masses. It is a universal force, so every particle of matter exerts a gravitational attraction on every other particle. The gravitational attraction is proportional to mass. The greater the mass, the stronger the force. Now, unfortunately, Newton does not give us a cause for this force. But before we simply dismiss Newton, let's recall that it is still the gravitational law that we use for most everyday phenomena, both on and off Earth. It is only when dealing with extremely large masses and densities that it is no longer valid. So unless gravitational fields are extremely strong, Newton's law is still a valid approximation. Our most complete and current theory of gravity is Einstein's general theory of relativity. Einstein gave us an entirely new way of understanding space, time, and gravity. According to his theory, gravity is a manifestation of the curvature of space, and the space-time curvature is determined by the content of space-time, or the mass-energy density at that point in space. The greater the density of the body, the greater the curvature, and therefore the greater the gravitational effect. So gravity is not really a force, at least not in the usual sense, but it is a warping of space-time. And what we perceive as gravity is just objects moving according to the geometry of space. So gravity is not just a simple attraction between masses, as Newton describes, but gravity is the interaction of matter and energy with the geometry of space and time. However, even though these are two different descriptions of gravity, we can see that in both theories, the greater the mass, the greater its influence. And that is key. Now, there are two important concepts related to gravity which we will often mention. The first is a gravitational field. We can define the gravitational field as a region of space generated by a massive body which influences the motion and behavior of another body. Recall that in our definition of a black hole, we mentioned a gravitational field so strong that nothing could escape. The next concept is a gravitational collapse. In a gravitational collapse, matter collapses in on itself under the effect of its own gravity. We will see that in most cases, the inward gravitational collapse is balanced by an outward pressure to stabilize the body from further collapsing. Okay, just a little bit more physics before we start our progression of events that will eventually lead us to black holes. We just need to be familiar with a few more terms and concepts that we will use throughout these lectures. The first concept is light. Light is an electromagnetic wave that travels through space at a constant speed. It travels at 300,000 kilometers per second, or in our more familiar units, 670 million miles per hour. Now here's a simple diagram of what is called the electromagnetic spectrum. We, humans, only see a small portion of the entire spectrum, called the optical or visible light. On one end, we have the high-energy gamma rays, X-rays, and ultraviolet. We can think of this as invisible light. On the other hand, we have the low-energy infrared, microwave, and radio waves. The next concept is mass. Mass is a little bit more difficult to define. For our purposes, we can think of mass as the amount of matter in an object. So the more matter an object has, the more massive it is. The next concept is density. Density is defined as mass per unit volume. So if you squeeze a very large mass into a very small volume, you get a very high density. Now, matter is made of atoms, so let's take a look at the basic atomic structure. Our three familiar subatomic particles are the proton, which is a positively charged particle, the neutron, which has zero net electric charge, in other words, it is electrically neutral, and the electron, which is a negatively charged particle. Now let's see these particles in an atom. The first is the hydrogen atom. Here we have a proton in the center and an electron in an orbital shell around the proton. This is the only atom that does not have a neutron. Next, we look at helium. Here we see two protons and two neutrons in the center and two electrons orbiting the center particles. The center of an atom is called the nucleus. Now, there is so much that can be said about atomic structure, but for these lectures, there are only two things that I'd like to focus on. First, the mass of the electron is so small that it is negligible compared to the proton and neutron, so the mass of an atom is simply the mass of its nucleus. The second thing to notice is that there is a lot of empty space between the nucleus and the outer electron shells. Now please note that this model is not to scale. As an example, if the nucleus were the size of a golf ball, then the outer shell would be 1 mile from the center. The point I'm trying to make is that most of the structure of the atom is empty space. So even the heaviest structures on Earth are basically empty space. As an example, if we were to take every atom that makes up the Empire State Building and remove all the empty space, it would be the size of a grain of rice. We will see that this is such an important concept when we talk about neutron stars and black holes. Our final concept is nuclear fusion. Nuclear fusion is the fusing together of lighter elements into heavier ones, and in the process, a huge amount of energy is released. This is the actual proton-proton chain reaction occurring in the sun's core. But we will look at a very simplified version. We start with 4 hydrogen nuclei, or simply 4 protons. Under the extreme high temperature, pressure, and density in the star's core, the 4 protons fuse together to form a helium nucleus, which is made up of 2 protons and 2 neutrons. And in the process, a huge amount of energy is released. But where does the energy come from? Well, it turns out that the mass of the helium nucleus is a little less than the mass of the original 4 hydrogen nuclei. This means that in the fusion process, a small amount of mass is lost. Now here is the beauty. That little bit of lost mass is converted into energy using E equals mc squared, Einstein's mass energy equivalence. Now, since the speed of light squared is a huge number, this tells us that a small amount of mass is equal to a very large amount of energy. Let's see an actual example. Every second, the sun converts about 600 million tons of hydrogen into 596 million tons of helium. That means that 4 million tons of mass is lost in the process. Now we plug 4 million tons into E equals mc squared, and what we get is 400 trillion watts. Now we all know that's a big number, but we really do not have an intuition for it. So in practical terms, this means that every second the sun puts out what 3 billion of our most powerful power plants would put out in a year. Now, as a reference, we currently have about 8,000 power plants in the US. And once again, every second the sun puts out what 3 billion of our most powerful power plants would put out in a year. That is absolutely amazing. But what's even more amazing is that the sun will continue to put out that amount of energy every second for the next 5 billion years. Okay, that's it for physics. Amazingly, this is all the physics you need to have a qualitative understanding of black holes. Okay, now that we've covered all our physics, let's start our progression of events that will eventually lead us to black holes. Since stellar black holes are the evolutionary endpoint of very massive stars, we will briefly cover the life cycle of stars with particular interest in their final stages. All stars start out as a gravitationally collapsing cloud of interstellar gas and dust, mostly hydrogen and helium, with a small percentage of heavier elements. The type of stars they become depends on the initial mass. An average star, such as our Sun, will live a fairly long life, fusing hydrogen into helium in its core. When it runs out of hydrogen, it will become a red giant. After the red giant phase, it will produce a beautiful planetary nebula and finally end up as a white dwarf and quietly fade away. More massive stars use up their fuel more quickly and therefore live shorter lives. As they run out of the fuel, they become red supergiants. And here is where they mainly differ from less massive stars. At the end of the red supergiant phase, they violently explode in a supernova, the remnants of which are either a neutron star or a black hole. So now let's briefly look at these stages in a bit more detail. For a more complete description of the stellar life cycle, please see my other lectures on stellar evolution found on this channel. For our brief look today, we start with where and how stars are born. Stars are born in immense clouds of interstellar gas and dust called nebulae, from the Latin word for cloud. This is a beautiful example called the Carina Nebula. You can see that some regions are denser than others. The darker areas indicate denser regions of gas and dust. Now, gravity goes to work within the cloud, bringing together material within the slightly denser regions of the cloud. Through gravity's relentless inward pull on surrounding material, denser regions become denser and denser. And as the material crushes inward, it gets hotter and hotter until the core is hot enough to start fusing hydrogen into helium. It is at this point that the star is born. Now, once a star is born, it begins its lifelong struggle against gravity. At each stage of their lives, stars are in hydrostatic equilibrium, where the inward gravitational collapse is balanced by some type of internal pressure that provides an outward force. During the main phase, we will see that the outward pressure is provided by nuclear fusion in the core. During the final stages, it is provided by quantum degeneracy pressures. We will see that a star's life and death depends on its initial mass, so the fate of a star is predetermined at birth. So let's take a look at the main phase of a star's life. As just mentioned, during a star's lifetime, it is constantly fighting against the relentless inward pull of gravity. The only thing a star can do to survive is to push back. So the inward gravitational collapse is balanced by the outward radiation pressure and heat generated by the nuclear fusion reactions in the core. Stars in this phase are called main sequence stars. This is the most stable phase in a star's life. They are happily fusing their abundance of hydrogen into helium. Here we see our main sequence star fusing hydrogen into helium in its core, which is surrounded by a shell of cooler hydrogen. Eventually, however, the hydrogen in the core will run out. In other words, all of the hydrogen in the core will eventually fuse into helium. At this point, the star starts to approach its final stages. The final state will depend on the initial mass of the star. So we start with a low to average mass star like our Sun. So once the hydrogen runs out, there will be no more nuclear reactions in the core. This means there will be no more outward pressure. So what happens? Gravity takes over, and the star will start to gravitationally collapse again. As it collapses, the temperature in the core increases until it is hot enough to start a new nuclear fusion reaction, fusing helium into carbon. When this happens, the star temporarily restabilizes, as the inward gravitational collapse is balanced by the outward radiation pressure generated by the new nuclear fusion process. So here we see the star's core fusing helium into carbon. The hot core is surrounded by a shell of hydrogen fusing into helium. Then we have the outer shell of non-fusing hydrogen. Now the heat from the core and the shell of fusing hydrogen push the cooler hydrogen shell outward, greatly expanding the size of the star. As a gas expands, it cools and its color shifts towards red. So our expanded star becomes what is known as a red giant. During this phase, our sun will expand out to the orbit of Mercury. Eventually, all the helium will also run out. And when that happens, once again, there will no longer be nuclear fusion reactions in the core. So the struggle continues. And with no more outward pressure, it's the same story. Gravity takes over. Just as before, the inward gravitational collapse will increase the temperature of the core, but this time there isn't enough mass to increase the temperature to start a new nuclear reaction. So there are no more nuclear reactions in the core. So what we have is an extremely hot and dense carbon core. The hot core is surrounded by fusing shells of helium into carbon and hydrogen into helium, pushing the outer shells even farther out. This is the second red giant phase, and our sun will likely expand out to the orbit of Earth. As the outer shell of hydrogen gas continues to expand, it becomes very loosely bound to the rest of the dying star. So as the gases continue to expand outward, we are left with a beautiful planetary nebula. Now, unlike their historically confusing name would suggest, a planetary nebula is a bubble of expanding gas surrounding a dead star. Stars can shed up more than half of their masses to the planetary nebula. As the planetary nebula expands, it disperses carbon into the surrounding space. Now, carbon is the key element for all known life on Earth. This is where most of the carbon comes from. The beautiful glowing colors are from ionized gases. And what is left of the original star is a very small and extremely hot and dense core called a white dwarf. So let's take a closer look at the stellar remnant known as a white dwarf. What remains of the once vibrant star is a very small, hot, dense, and inert core. It is an inert core because at this point there are no more nuclear reactions in the core. In other words, the star is dead. Now, if there are no more nuclear reactions in the core, what balances the gravitational collapse to allow it to be in a stable configuration? The answer is electron degeneracy pressure. This pressure is associated with quantum behavior of particles. Now, to understand this, we briefly look at two principles. The first is the Pauli exclusion principle. This tells us that no two identical electrons, or more generally two fermions, can occupy the same quantum state. Essentially what this means is that electrons cannot stack up onto each other at the lowest energy level. They must reside in separate energy levels. Now, in a white dwarf, matter is compressed to such high density that the electrons are squeezed in as close as they can be while still obeying the Pauli exclusion principle. In other words, they are squeezed in as much as they can quantum mechanically be. Which brings us to the second principle, the Heisenberg uncertainty principle. This principle states that it is not possible to simultaneously know the exact position and speed of a particle. The equation essentially tells us that the uncertainty in a particle's position, delta x, times the uncertainty in its momentum, delta p, is a constant. So neither of the two uncertainties can be zero. This equation also tells us that as one uncertainty decreases, the other must increase. This means that the tighter the electrons are confined to smaller and smaller space, in other words, the uncertainty of its position decreases, the larger the spread of possible speeds. And the larger the speed of a particle, the greater the pressure. So in a white dwarf, electrons are squeezed in so tightly that they must move around very fast, and therefore provide the outward pressure to maintain the white dwarf in hydrostatic equilibrium against the inward gravitational collapse. Now, I've mentioned a few times that these white dwarfs are extremely dense. So how dense are we talking about? Well, our sun will shed about half of its mass to its planetary nebula. The remaining half will contract into a white dwarf about the size of Earth. Now, the sun's mass is 300,000 times the mass of the Earth. So that means that 150,000 times the mass of the Earth gets squeezed into an object the size of Earth. Okay, so how dense is a white dwarf? Well, 1 teaspoon of white dwarf matter on Earth would weigh 5 tons. So this is pretty dense stuff. But there is a limit of how dense a white dwarf can be. So let's start with a little history. The first white dwarf was discovered in the triple star system 40 Eridani by William Herschel, although at the time he had no way of knowing that this was a very unusual star. Now, for the Star Trek fans out there, yes, this is the same star system of Spock's homeworld, Vulcan. The next to be discovered was Sirius B, a companion to Sirius, the brightest star in the night sky. Now, although these are now both recognized as white dwarfs, it wasn't until the early 1900s that the nature of these very dense objects was known. The expert on stellar evolution in the 1920s was Sir Arthur Eddington. He popularized the term white dwarf and theorized that they could be the endpoint for the life cycle of all stars. However, he did not have an explanation for how this final stage of a star would hold up against any further gravitational collapse. In 1926, Ralph Fowler solved this puzzle by applying the two quantum concepts of the uncertainty and the exclusion principles to Sirius B. But the name that will be forever associated with white dwarfs is Subrahmanyan Chandrasekhar. Chandrasekhar was born in India in 1910, and at the young age of 19, he was awarded a scholarship to Trinity College, Cambridge, for his PhD. Now, during his sea voyage to England, he studied Fowler's paper on quantum mechanics applied to white dwarfs, and made a remarkable discovery. Unlike Fowler, Chandrasekhar calculated how large the speed of the electrons would actually be, and he realized that they would be moving around close to the speed of light. So, in addition to quantum mechanical effects, Chandra applied Einstein's special relativity as well. What he found was that if a white dwarf became too dense, the electrons would be unable to sustain the gravitational collapse. In other words, there is a maximum mass limit beyond which electron degeneracy pressure can no longer hold back gravity, and the star will continue to collapse. Arthur Eddington refused to accept this result, but Chandra would eventually be proven correct and was awarded the 1983 Nobel Prize in Physics. The maximum mass limit of a white dwarf is called the Chandrasekhar limit, and is equal to 1.4 solar masses. Now let's see what happens to more massive stars. As mentioned before, the fate of a star depends on its initial mass, also referred to as its birth mass. So the fate of a star is preordained at birth. If the initial mass is between 1/10 the mass of the Sun and 8 times the mass of the Sun, then the star will die quietly as a white dwarf, as we just saw. If the initial mass is greater than 10 solar masses, the star will die a violent death known as a supernova. Now, stars caught somewhere between 8 and 10 solar masses will either lose part of their outer envelope and become a white dwarf, or accrete additional material and undergo a core collapse to a neutron star. So a supernova is the explosion of a massive star towards the end of its life cycle. We will see that the remnants of supernovae are neutron stars and black holes. Now, stars are basically huge nuclear furnaces producing elements up to iron in their cores. So how are the elements formed in the core of stars? Recall that during its lifetime, an average star or a sun-like star will have gone through 2 nuclear fusion processes. First, fusing hydrogen into helium, then when the hydrogen runs out, the star collapses until the core is hot enough to start its second fusion phase, fusing helium into carbon. Once all the helium is used up, the star starts to collapse again. The core's temperature increases, but there isn't enough mass to continue the collapse. So we are left with a carbon core surrounded by a shell of helium fusing into carbon and a shell of hydrogen fusing into helium, and finally a non-fusing shell of hydrogen. But in the case of more massive stars, this fusion process continues. We see the process of core collapse and ignition of new nuclear fusion reactions continue while producing heavier and heavier elements until it reaches iron. So these massive stars undergo multiple periods of stability, core collapse, stability, and core collapse. Right before the star explodes, it has this onion-like structure with an inert iron core and shells of fusing elements surrounding the core. So here we have the inert iron core surrounded by shells of fusing elements. Now here is a core collapse timeline for a star that is 25 times the mass of our Sun. Now our Sun's hydrogen fusion phase will last 10 billion years. For this star, it lasts only 7 million years. And as you can see, each successive stage takes shorter and shorter time, with silicon taking just 1 day to fuse to iron. In the next slide, we will see that the catastrophic core collapse right before the explosion occurs in just a fraction of a second. So now we take a look at why stars explode when they reach this stage. This is our massive star with an iron core surrounded by shells of fusing elements. After all the silicon has fused into iron in the core, we are left with an iron core. No further nuclear reactions can occur at this stage because the fusion of iron would absorb energy rather than release energy as in previous reactions. So at this point, the iron core continues to build up from the surrounding shell of fusing silicon. As more and more iron is added to the core, it becomes denser and denser. Now at this point, the iron still has an atomic structure with a nucleus and surrounding electrons. The electrons are getting squeezed tighter and tighter, and they are doing their best to maintain the structure. But at a certain point, the electrons finally give up, and the core undergoes a catastrophic core collapse, collapsing to its maximum state of density. As the core collapses in just a fraction of a second, the outer layers are left with nothing to support them. So they fall inward and rebound off the collapsed core, propagating outward, producing a shock wave, and the star explodes. During this explosion, the elements that were in the outer shells get blown out into the universe. The supernova explosion releases so much energy that heavier elements, those beyond iron, are now formed through the high-energy particle and nuclear reactions. These elements are dispersed throughout the universe and make up the clouds of interstellar gas and dust from which other stars and their planetary systems are formed. Indeed, our own home planet Earth was formed by elements that were first produced in stars billions of years ago. This is an animation of a supernova explosion with a fade into a real image of the Crab Nebula. So let's take a look. And here it is as seen by the Hubble Space Telescope. It is the supernova remnant known as the Crab Nebula. It is the most famous remnant of a supernova. The supernova itself was observed by Chinese astronomers in 1054 AD, and they called it a guest star. This new star was visible for 23 days during the daytime and for almost 2 years in the night sky. This is what is left over from the explosion and is what we see 1,000 years after the observed explosion. Almost 1,000 years after the star initially exploded, the nebula is still expanding at a rate of about 1 mile per second. Now, as mentioned, this image was taken by the Hubble Space Telescope, so it's in the visible range. Notice that the center of the image appears a bit hazy. So let's take a look at it in different wavelengths of light. This is a composite image of the nebula taken by the 3 NASA space telescopes. Now we can clearly see something in the center of the nebula. The center blue image is X-ray radiation, and at the very center we have a neutron star. So a neutron star, therefore, is the stellar remnant of a very massive star. What is left over of the star has collapsed into an extremely dense core. Right before the catastrophic collapse, the core still had iron nuclei and electrons squeezed in as tight as they could possibly be. The iron core was held up by electron degeneracy pressure. But the mass is so large that the gravitational collapse is so strong that the electrons finally give up. They penetrate the nucleus, merging with protons and forming neutrons. What remains is an extremely dense core called a neutron star. The typical neutron star has a mass of around 1.5 times the mass of the Sun, all condensed into an object that's about 12 miles across. The outer crust of the star is thought to be a thin crust of iron, while the inner portion is basically all neutrons. It is called a fluid because the particles are all closely packed, but do not have a regular pattern or structure. We will see that this is an extremely dense fluid. Now, the properties of such high-density matter are still not precisely known, but let's get a basic understanding. So why are neutron stars so dense? And what do we mean by a fluid neutron core? Well, we start with looking at regular atomic matter. Recall that all the mass of an atom is contained in the nucleus, with the tiny electrons in various shells surrounding the nucleus. As you can see, most of the atom is empty space. And once again, this is not to scale. If the nucleus were the size of a golf ball, the outer shell of electrons would be 2 miles in diameter. So atoms are basically all empty space, except for the very small nucleus at the center. It is the electron shells that maintain the outer structure of the atom. Now, under the extremely high pressure conditions in the core right before the collapse, the electrons are squeezed in as tight as they can quantum mechanically get. But eventually, the gravitational pressure is just too much. The electron degeneracy pressure is overcome, and the electrons finally give up, and the whole atomic structure collapses, allowing the electrons to penetrate the nucleus. In the nucleus, the negatively charged electrons merge with the positively charged protons and combine to become neutrons. And in the process, an elementary particle called a neutrino is also emitted. So now there is no more empty space. We just have a bunch of extremely tightly packed neutrons. This is the densest state of matter that we know. It is called neutron degenerate matter. There is also a hypothetical denser state of matter called quark degenerate matter, which would be made up of hypothetical quark stars. And as we will see, a black hole is even denser, but it is a state of matter that our current laws of physics cannot describe. The interior of a neutron star is still not well understood and is the subject of active research. It is thought that below a very thin atmosphere of hydrogen and helium, there is an outer crust less than an inch thick, made of electrons bound to atomic nuclei, possibly iron. Moving inward, there are likely different layers of increasing density. Okay, so what does all this talk about density translate to? Well, if we take 1 teaspoon of Earth, it would weigh about 1 ounce. Recall that a white dwarf is a star with a mass of approximately 1/2 the mass of the Sun and is squeezed into an object the size of Earth. The mass of the Sun is 300,000 times the mass of the Earth, so we take something that is 150,000 times the mass of the Earth and squeeze it into the size of Earth, and if we could take 1 teaspoon of white dwarf matter, it would weigh 5 tons. Now with a neutron star, we take something that is 1.5 times the mass of the Sun, or 450,000 times the mass of the Earth, and squeeze it into an object that is only 12 miles in diameter. Now this neutron star is not to scale. Earth is 8,000 miles in diameter, so the neutron star would just be a dot, or about the size of a city. If we could take 1 teaspoon of neutron star, it would weigh 4 billion tons. That's about 600 pyramids of Giza in 1 teaspoon. So hopefully you are starting to get a better idea of what we mean by matter compressed to such high density. So neutron stars are extremely dense. But is there an upper limit like the Chandrasekhar limit for white dwarfs? And the answer is yes. First of all, what holds up the neutron star against the relentless inward pull of gravity? It is the combination of neutron degeneracy pressure, similar to electron degeneracy pressure in white dwarfs, and the strong nuclear force between neutrons, which is usually an attractive force, but when particles are so tightly packed together, it becomes repulsive. With all that said, the interior of neutron star is still not well understood. It is likely that they are not simply an ultra-dense neutron fluid as depicted here, but there may be layers of matter becoming denser and denser as it gets closer to the inner core. Although we still do not know the state of matter of the inner core, it is the final stable form of matter short of becoming a black hole. This is still a very active area of research. In the late 1930s, Robert Oppenheimer became intrigued by the whole concept of neutron stars, whose existence was first proposed by the Swiss-American astronomer Fritz Zwicky in the early 1930s. Oppenheimer began investigating the quantum effects of matter at such high densities. He wanted to find out if neutron stars were truly the end stage of stellar collapse. Oppenheimer realized that he had to apply general relativity to neutron stars because they were so dense that their strong gravitational field could not be described by Newtonian gravity. His calculations, along with his student George Volkoff, and using previous work by Richard Tolman, showed that there is a maximum mass beyond which the neutron star cannot resist the gravitational collapse. Today's current observations put the mass limit, or the TOV limit, at 2.16 solar masses. Essentially, what Oppenheimer showed is that if a star is big and dense enough, it will implode indefinitely and collapse right out of sight. We will talk more about this in the next lecture. As we end today's lecture, let's take a brief look at the discovery of neutron stars. As we've just seen, neutron stars were theoretically predicted in the 1930s, but were not discovered until 40 years later in 1967 by graduate student Jocelyn Bell in the form of pulsars. Jocelyn Bell discovered objects in the sky that appeared to have pulses of radiation coming from them at very regular intervals. As an example, the neutron star in the Crab Nebula is a pulsar that pulses 30 times per second. Now, at first, no one knew the source of this radiation, and some even thought that it might be extraterrestrial communications from other intelligent life in the universe, and jokingly called them LGMs, for little green men. But they quickly figured out that they were rapidly rotating, highly magnetized neutron stars. Here we see a neutron star spinning on its axis. And just like the Earth's magnetic field, we have magnetic field lines going from one magnetic pole to the other. Now, charged particles are accelerated along the magnetic axis, producing a radiation beam. This is the radiation beam that we see. Now, the easiest example to explain the effect of a pulsar is a lighthouse. The light in a lighthouse is always on, but we only see it when it intersects our line of sight. So a lighthouse appears to pulse at regular intervals, but it is just because it is rotating. And so it is with pulsars. A pulsar is a rapidly rotating neutron star, and we see a pulse of radiation every time the beam sweeps by Earth. And so we've set the stage. We've talked about gravity, both in our everyday intuitive sense, as described by Newton, and in Einstein's less intuitive but more complete description of gravity as the curvature of space-time. Then we talked about the implosion of stars as they collapse at the end of their lives. An average star, such as our Sun, will collapse to a very dense object known as a white dwarf. A more massive star will collapse even further into an even denser object known as a neutron star. In the next lecture, we will see how even more massive stars will implode and collapse completely under their own gravity, producing stellar black holes. We will see that black holes distort space-time so strongly that parts of the universe are forever hidden from the rest. And then we will talk about gravitational waves, first discovered from the merger of two stellar black holes. I hope you've enjoyed the first lecture in this series. Hope to see you next time, and thank you for watching.